Take a good look at this. Every star you can see on a clear night, every swirling galaxy captured by our most powerful telescopes, all of it is contained within this single, shimmering sphere of light. This is our home, the observable universe, a cosmic bubble over 90 billion light-years across, containing hundreds of billions of galaxies. But what you're really seeing is a story with a hard edge, a definite limit to everything we can ever know. And it forces upon us a single, haunting question that has captivated thinkers for centuries. When we finally reach that boundary, what do we find waiting in the dark? Is there something, or is there nothing at all? This isn't just an astronomical curiosity. It's the ultimate expression of human wonder, the final frontier of our imagination pushing against the very limits of reality itself. Today, we are going on a journey to the edge of everything. We will venture past the farthest quasars, beyond the cosmic microwave background, and step right up to that final veil to peer into the absolute unknown. To guide us, we have assembled 25 of the most incredible, mind-bending theories that science and philosophy have to offer. Some are grounded in the latest cosmological models, the rigorous work of physicists grappling with multidimensional math and quantum gravity. Others are pure flights of philosophical speculation, ideas so vast and strange they challenge our very understanding of what existence even means. Each one is a potential key to the greatest mystery of all. This exploration is more than a list of ideas. It is a map of human curiosity itself. It's about that deep, intrinsic need to know what's over the next hill, even when that hill is the edge of the cosmos. From the chilling possibility of an infinite void to the breathtaking concept of a multiverse teeming with alternate realities, we will navigate a landscape of thought where the rules of physics as we know them break down and imagination takes the lead. So prepare to have your concept of reality stretched, twisted, and reshaped as we count down 25 theories about what truly lies beyond our universe. Our journey begins with perhaps the most famous and far-reaching idea in all of modern cosmology, the multiverse. It's a concept that suggests the stunning expanse we call our universe, with its hundreds of billions of galaxies, might not be the entirety of existence. Instead, it could be just one single bubble in an immeasurably vast cosmic foam, a single page in an infinite book of realities. Each of these other universes could be a realm with its own unique, and often wildly different set of physical laws. In one, gravity might be 10 times stronger, making planets the size of marbles but with the weight of stars. In another, the fundamental forces that bind atoms together might be too weak, preventing matter from ever coalescing into stars and galaxies, leaving a dark, featureless expanse. Life as we know it would be impossible in almost all of them, making our universe not necessarily special or designed, but simply one of the rare habitable pockets in a sprawling cosmic archipelago. This grand vision of the multiverse isn't just a single, monolithic theory. It actually comes in several distinct flavors, each emerging from different corners of physics. One of the leading contenders is the inflationary multiverse. This idea springs from the theory of cosmic inflation, which describes how our universe underwent an unimaginably rapid expansion in the first fraction of a second after the Big Bang. The concept of eternal inflation proposes that this explosive expansion never truly stopped everywhere. Instead, it suggests that the overall fabric of space-time continues to inflate at an accelerating rate forever. Within this ever-stretching background, random quantum fluctuations can cause localized pockets to stop inflating and pinch off to form their own separate, self-contained bubble universes. Our entire cosmos would be just one such bubble in an endless, frothing sea of creation, where new universes are constantly budding off from the inflationary background, each with a random and unique set of physical constants. A completely different path to the multiverse comes not from cosmology, but from the bizarre and counterintuitive world of quantum mechanics. This is the quantum multiverse, most famously articulated by the many worlds interpretation. In standard quantum theory, a particle exists in a blurry state of all possible positions, called a superposition, until it is observed and chooses a single, definite state. The many worlds interpretation offers a radical solution to this quantum weirdness. It proposes that every time a quantum event has multiple possible outcomes, the universe doesn't choose one. Instead, it splits into multiple branches, with each and every possible outcome actually occurring in its own newly created parallel reality. In one universe, you might be watching this video right now, while in another, you decided to click on a different one entirely. Every decision, every random quantum event spawns new timelines, creating a near-infinite tree of alternate histories and futures. While this inflationary version gives us a landscape of universes with different laws, the quantum multiverse gives us endless variations of our own universe, where every possibility is not just imagined but physically real. While the inflationary and quantum multiverses paint a picture of endless cosmic bubbles and branching timelines, a third and perhaps even more profound version emerges from the most ambitious attempt in physics to unify all the forces of nature, string theory. This approach gives us the landscape multiverse, a concept that directly addresses why our universe seems so perfectly tailored for life. According to string theory, the fundamental building blocks of reality are not point-like particles but incredibly tiny, vibrating strings. The specific way these strings vibrate determines what kind of particle they manifest as an electron, a quark, or a photon. But for the math of string theory to work, it requires more than the three spatial dimensions and one time dimension we experience. It demands extra dimensions of space, as many as 6 or 7 more, all curled up into shapes far too small for us to perceive. The key to the landscape multiverse lies in the way these extra dimensions can fold and twist upon themselves. Think of it like this: a simple, identical strand of wire can be bent and shaped into countless different sculptures, each with a unique form. In a similar way, the extra dimensions in string theory can settle into an enormous number of stable configurations, perhaps as many as 10 to the power of 500 different possibilities. Each of these distinct geometric shapes is called a vacuum state, and each one corresponds to a completely different set of physical laws and constants for a universe. The strength of gravity, the mass of an electron, the power of the nuclear forces, all of these fundamental properties would be locked in by the specific, frozen geometry of the hidden dimensions. This is where the concept of the landscape gets its name. It's not a physical terrain of hills and valleys, but a vast, abstract topography of possibilities. Our universe, with its specific, life-permitting constants, would simply occupy one tiny, fertile valley in this colossal cosmic landscape. The vast majority of other valleys would represent universes that are utterly sterile and lifeless. In some, gravity might be so strong that any star that formed would immediately collapse into a black hole. In others, the electromagnetic force might be too weak to hold atoms together, preventing chemistry from ever occurring. Our existence here isn't evidence of a grand design, but rather a consequence of sheer, mind-numbing statistics. With so many possible universes on the landscape, it's almost inevitable that at least a few would, by pure chance, have the right combination of laws to allow for stars, planets, and life to emerge. We, quite simply, had to find ourselves in one of the habitable ones. This perspective transforms our place in the cosmos from a central, special creation into a fortunate, but ultimately random, address in a multiverse of unimaginable scale and variety. But what if the barrier between our universe and another isn't a distant, unreachable horizon, but a divide so thin we could, in theory, reach out and touch it? This brings us to a theory that redefines the very meaning of parallel, suggesting that another entire cosmos could be hovering just a fraction of a millimeter away from our own, separated not by vast stretches of space, but by a dimension our senses are blind to. This is the world of branes and the bulk, a mind-bending vision born from the depths of string theory and its more powerful successor, M-theory. To understand this, we first need to reimagine the fabric of our own reality. We are intimately familiar with the three dimensions of space: length, width, and height, and the one dimension of time, but what if that's not the whole story? What if there are more spatial dimensions, realms of direction that are curled up so incredibly tiny, or are so expansive that our matter is simply stuck, unable to move into them? This is the core of the brane world scenario. In this model, our entire universe, every galaxy, every star, every one of us is not floating freely in a void. Instead, it is confined to the surface of a vast three-dimensional membrane, or brane for short. Think of it like a single, impossibly thin page in a gigantic, multidimensional book. We are like ink on that page. We can move freely across its length and width, but we are utterly trapped within its flat surface, completely unaware of the other pages stacked just above and below us. The space that contains all these floating branes is known as the bulk. This higher dimensional arena is the true, full reality, and our brane is just one object drifting within it. This leads to a profound and elegant explanation for one of physics' most stubborn mysteries. Why is gravity so unimaginably weaker than all the other fundamental forces? Consider that a small fridge magnet can generate enough electromagnetic force to defy the gravitational pull of the entire planet Earth. In the brane world picture, the answer is that while the particles that make up you, me, and everything we see, quarks, electrons, photons, are permanently stuck to our brane, gravity is different. Gravity, in the form of gravitons, is not confined. It is the only force that can leak out, spreading its influence into the extra dimensions of the bulk. This dilution effect would make gravity appear exceptionally weak from our perspective, trapped on the brane, just as the light from a single bulb seems dim when it has to illuminate an enormous cavern instead of a small room. The most stunning implication of all this is the possibility of other branes. If our universe is one three-dimensional membrane, then there could be countless others, each a self-contained universe with its own stars, its own galaxies, and potentially its own laws of physics, all floating parallel to us in the bulk. The distance to these parallel worlds wouldn't be measured in light years, but in the unseen millimeters or even smaller scales of these extra dimensions. They could be right next to us, a mirror cosmos separated by a gap our technology cannot yet cross. And sometimes these branes adrift in the bulk might not remain peacefully separate. They could be drawn together, weaving through the higher dimensional space until they collide. The energy released in such a cataclysmic collision would be beyond comprehension, potentially providing the raw, explosive ignition for a whole new cosmic cycle. Some physicists have proposed that our own Big Bang was not a singular point of creation from nothing, but the aftermath of just such a violent encounter between two branes, a cosmic accident in a much larger and far more crowded multidimensional arena. But what if the story of our universe isn't a one-act play, beginning with a single explosive moment and ending in cold, dark silence? What if, instead of a linear march from birth to death, the cosmos is engaged in an eternal, rhythmic dance of destruction and creation? This brings us to our third theory, a vision of a universe without true beginning or end, the cyclic model. This idea challenges the very notion of the Big Bang as a unique starting point, proposing instead that it was merely the latest in an endless series of cosmic rebirths, a dramatic turning point in a cycle that has repeated countless times in the past and will continue countless times into the future. One of the most compelling versions of this idea is known as the ekpyrotic universe, a name derived from the ancient Greek word for conflagration or out of fire. It beautifully merges the brane world concept we just explored with this cyclical vision. Picture our three-dimensional brane, our home universe, floating in the bulk alongside another parallel brane. Rather than existing in static isolation, these two cosmic membranes are drawn together by an invisible force, perhaps a kind of spring-like tension in the higher dimensional space. They approach each other slowly over trillions of years and eventually collide. This collision is not a gentle bump. It is a cataclysmic event of unimaginable energy, an impact that floods our brain with radiation and matter, effectively resetting the cosmic clock. This violent encounter, from our perspective trapped on the brain, would look exactly like a hot, dense Big Bang. In this model, the Big Bang was not the beginning of time and space, but a phase transition, a turnover from a period of contraction and collision into a new period of expansion and evolution. This leads to a profound and deeply humbling consequence. Each cycle, from collision to collision, effectively acts as a cosmic reset button. As the universe expands after the bang, it gives rise to all the structures we see today: galaxies, stars, planets, and life. But this expansion eventually slows, stops, and reverses into a long, gradual contraction. During this contraction phase, as all matter and energy are pulled back together, the universe is essentially put through a cosmic blender. Galaxies merge and are torn apart, stars are vaporized, and even black holes eventually evaporate. The vast majority of the information that defined the previous cycle, the specific arrangement of galaxies, the patterns of life, the entire history of that cosmic era is scrambled and erased. It's like writing a detailed story in the sand on a beach, only for the tide to come in, washing the slate clean. When the next collision occurs and a new universe is born, it starts with a clean, hot, and nearly uniform state, inheriting only the most fundamental parameters from the previous cycle but none of its specific history. Each new universe is a fresh start, a blank canvas upon which a completely new cosmic story can be written, with new galaxies, new stars, and potentially new life arising from the ashes of the old. Yet, for all the grandeur of colliding branes and cyclical rebirth, one of the most disorienting theories proposes that the very nature of our reality is an elaborate illusion. This is the holographic principle, an idea so radical it suggests that the three-dimensional world we inhabit, the depth of space, the solidity of matter, is nothing more than a magnificent projection, a cosmic hologram. To understand how such a mind-bending concept could possibly be taken seriously, we have to venture not to the edge of the observable universe, but to the boundary of one of its most enigmatic objects, a black hole. The story begins in the 1970s with a young physicist named Jacob Bekenstein and his mentor, the legendary Stephen Hawking. Hawking had made the startling discovery that black holes are not completely black. Due to quantum effects at their boundary, they slowly radiate energy and evaporate over astronomical timescales. This created a profound puzzle known as the black hole information paradox. In physics, information, the specific arrangement of every particle, is fundamentally conserved. It can't be truly destroyed, but if a black hole evaporates completely, what happens to all the information about the stars, planets, and atoms that fell into it? Does it just vanish, violating a cornerstone principle of quantum mechanics? Bekenstein made a crucial connection. He realized that the amount of information a black hole can contain is not proportional to its volume, as you might expect for a three-dimensional object, but to the surface area of its event horizon, the two-dimensional spherical boundary from which not even light can escape. Think of it like this: a typical storage device, like a hard drive, holds information in its volume. The more cubic space you have, the more data you can store. But a black hole behaves as if all the data about everything inside it is somehow encoded, pixel by pixel, on the surface of its event horizon. This was the first hint that the universe might play by a very different set of rules when it comes to information, prioritizing a two-dimensional surface over a three-dimensional volume. This insight was later formalized by physicists like Gerard T. Hooft and Leonard Susskind into the full holographic principle. They proposed that this isn't just a quirky property of black holes, it could be a fundamental feature of the entire cosmos. In this view, our entire observable universe, with its countless galaxies and vast expanses, could be a holographic projection originating from a two-dimensional surface that lies at the cosmic horizon, the absolute limit of what we can see. All the information needed to describe every particle, every force, and every event within our three-dimensional reality is stored on this distant, flat surface, much like the data on a Blu-ray disc encodes a rich three-dimensional movie. We are not the actors on the stage, we are the movie being projected from the cosmic projector at the edge of everything. So, what would this mean for our original question, what lies beyond the universe? In the holographic framework, the answer is both simple and utterly strange. There is no beyond in the way we typically imagine it. You cannot travel past the edge to find new galaxies or other universes. Instead, if you were to somehow reach that ultimate boundary, you would simply find a cold, dark, two-dimensional surface, buzzing with an unimaginable density of encoded information. This surface is the source code of our reality. The three-dimensional world we experience, with its rich tapestry of stars, planets, and life, is a kind of emergent illusion, a translation of that two-dimensional data into the immersive experience of space and time. It is the ultimate statement that appearances can be deceiving, and that the true nature of reality may be written in a language of information on a canvas we have only just begun to perceive. Now, let's take a radical turn from the holographic principle and consider a theory that is perhaps even more unsettling. The idea that our entire cosmos, from the farthest galaxy to the very thoughts in your head, is not a fundamental reality at all, but an elaborate digital construct. This is the simulation hypothesis, a provocative proposal suggesting that what we experience as the universe is actually an advanced computer simulation, a kind of hyper-realistic video game being run by a civilization of post-human beings, whose technological capabilities are so far beyond our own that they are indistinguishable from what we might call magic. This concept, popularized by figures like philosopher Nick Bostrom, is built on a logical and deeply philosophical trilemma. The argument often begins with the assumption that a sufficiently advanced civilization would have both the immense computing power and the potential motivation, perhaps for scientific research, entertainment, or historical preservation, to create detailed simulations of their own ancestors. Given that possibility, Bostrom posits that at least one of the following three propositions must be true. First, that virtually all civilizations like ours go extinct before reaching such a post-human stage of technological maturity. Second, that even if they reach that stage, they have exactly zero interest in running ancestral simulations. Or third, that we are almost certainly living such a simulation right now. If you believe the first two are unlikely, that some civilizations will survive and that at least some of them will run simulations, then the statistical weight tips heavily in favor of the third option. There would be, by sheer numbers, vastly more simulated minds than base-level biological ones, making it far more probable that your own mind is one of the simulated ones. Beyond this philosophical reasoning, some scientists and thinkers point to potential glitches in our reality that could be interpreted as artifacts of the underlying code. One such clue might lie in the fundamental graininess of the universe. Just as a digital image, when magnified enough, reveals its underlying pixel structure, our space-time appears to have a minimum possible unit of distance known as the Planck length. This is an inconceivably tiny scale, about 10 to the power of 35 times smaller than a meter, below which the concepts of space and distance cease to have any meaning. Similarly, there is a smallest unit of time, the Planck time. This inherent quantization, this pixelation of reality, is exactly what you would expect from a digital simulation running on a computer with finite, albeit astronomically large, processing power and memory. The universe isn't running on an infinitely smooth, continuous fabric, but appears to be rendered in discrete, tiny chunks. Another potential piece of evidence that simulation theorists point to is the curious fine-tuning of the universe's physical constants. Why do the fundamental forces gravity, electromagnetism, and the nuclear forces have the exact, precise strengths that they do? If the force of gravity were even slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, galaxies and stars could never have formed. The mass of the electron, the strength of the strong nuclear force that binds atomic nuclei together. All of these values seem perfectly calibrated to allow for the existence of complex chemistry, long-lived stars, and ultimately, life. In a natural, undesigned universe, this appears to be an astonishingly unlikely coincidence. But from a simulation perspective, this fine-tuning could be seen as a form of intentional parameter setting. A programmer aiming to create a stable and interesting simulation capable of generating complex structures like stars, planets, and observers would need to dial in these constants very carefully. The laws of physics in our universe, then, might not be fundamental truths of nature, but rather the carefully chosen and optimized rules of the simulation, designed to produce a rich and evolving virtual world. Pondering the nature of the world outside our simulation leads to dizzying speculation. What would the civilization running this cosmic program be like? They would exist in what we would have to call the base reality, a universe operating at a level of existence more fundamental than our own. Their physics would be the true, underlying physics, and their technology would allow them to manipulate reality in ways we can barely imagine. They might be our direct descendants, a future version of humanity that has survived for millennia and now runs simulations of its own past as a form of historical study or entertainment. Or they could be a completely alien intelligence whose motives and nature are entirely beyond our comprehension. The very laws of logic and causality that govern our simulated world might not apply in their base reality, meaning we have no framework to even begin to understand their intentions. Are we part of a grand scientific experiment? Are we characters in an unfathomably complex game? Or are we merely digital ghosts in a cosmic archive, a preserved record of a civilization that long ago turned to dust in its own, now vanished real world? The simulation hypothesis doesn't just challenge our place in the cosmos. It challenges the very authenticity of our existence, leaving us to wonder if the stars we gaze upon are merely pixels in a display, and the vastness of space is nothing more than allocated memory in a computer of godlike power. Having explored the digital frontier of the simulation hypothesis, we now return to the bedrock of modern cosmology with a theory that is both foundational and revolutionary. This is the concept of cosmic inflation, a powerful idea that not only explains the large-scale structure of our universe, but also provides one of the most compelling mechanisms for generating a multiverse. To understand this, we must travel back to the very first moments of existence, to a time so inconceivably brief that the entire cosmos was smaller than a single proton. The standard Big Bang theory, for all its success, left some puzzling questions unanswered. Why is the universe so remarkably uniform in all directions? Distant regions of space on opposite sides of the sky have the same temperature and density, yet in a cosmos expanding from a single point, these regions would never have had time to exchange heat or information. It's as if thousands of people in a vast, crowded stadium without any communication all decided to stand up and sing the same song in perfect unison at the exact same moment. Cosmic inflation solves this riddle by proposing a breathtaking prelude to the traditional Big Bang. Imagine the nascent universe was filled with a peculiar form of energy, a field that generated a powerful repulsive gravity. This energy caused space itself to undergo a period of hyper-expansion, ballooning in size by a factor of trillions upon trillions in a vanishingly small fraction of a second. This explosive stretching smoothed out the cosmos, ironing out any initial wrinkles or irregularities, and left it large, flat, and incredibly uniform, just as we observe it today. Once this inflationary energy decayed, it transformed into the hot, dense soup of particles and radiation that define the conventional Big Bang, setting the stage for the formation of everything we see. This elegant process explains the smoothness, the flatness, and even the origin of the tiny seeds that would later grow into galaxies, but the story doesn't end there. The most profound implication of inflation arises when we consider a specific version of the theory known as eternal chaotic inflation. In this picture, the process of inflationary expansion never completely shuts off everywhere at once. Think of it like a pot of water coming to a rolling boil. The overall state is one of furious activity, but within that, individual bubbles of steam constantly form, rise, and pop. In the cosmic context, the background of spacetime continues to inflate at an accelerating rate forever, acting like the boiling water. However, within this eternally stretching fabric, random quantum fluctuations can cause localized pockets to lose their inflationary energy, causing that rapid expansion to slow and stop. Each of these regions then pinches off to form its own separate, self-contained bubble universe, adrift in the endlessly inflating background. Our entire observable cosmos, with its hundreds of billions of galaxies, is likely just one such bubble. We live inside a pocket where inflation ended, allowing for the peaceful formation of stars and planets. But beyond our cosmic horizon, the grand inflationary engine continues to roar, constantly giving birth to new bubble universes in an endless, frothing sea of creation. Each of these new realms could have vastly different properties. The process that ended inflation in our bubble and set our specific laws of physics in place might have played out differently elsewhere. One neighboring bubble might have much stronger nuclear forces, leading to a universe filled with strange, heavy elements and no stable hydrogen for stars. Another might have a different number of spatial dimensions, making geometry and motion as we know them impossible. We are not at the center of anything. We are simply one island in an infinite cosmic archipelago, with new islands constantly emerging from the quantum foam of the eternal inflationary sea. This vision transforms the Big Bang from a unique moment of creation into a local event, a single blossom on an infinite tree of reality whose roots lie deep in the process of eternal inflation. If the idea of a simulated reality feels like a profound departure from classical physics, prepare for a theory that pushes the boundaries of ontology even further. This is the mathematical universe hypothesis championed by physicist Max Tegmark, and it proposes a truly radical idea. Our physical reality isn't just conveniently described by the language of mathematics, it is mathematics. In this view, the universe and everything in it isn't merely running on equations like a computer simulation. It is an equation, or more precisely, a specific, self-consistent mathematical structure. The atoms, the forces, the very fabric of space-time are not fundamental. They are just shadows, manifestations of an underlying, abstract mathematical form. To grasp this, consider a simple, perfect circle. You can't hold a perfect circle in your hand. Any physical drawing of one is just an approximation, a collection of atoms that is only roughly circular. But the mathematical idea of a circle, defined as all points equidistant from a center, is perfect, eternal, and exists entirely independently of any physical reality. It has properties, a circumference, an area. It is a complete, self-contained structure in the abstract realm of mathematics. The mathematical universe hypothesis takes this concept and scales it up to a breathtaking degree. It posits that our entire cosmos is akin to that perfect circle. The universe we perceive is simply the physical instantiation of an incredibly complex, self-consistent mathematical structure. We don't live in a universe that follows mathematical rules. We live inside a mathematical object. This leads to an inevitable and staggering consequence for what lies beyond our cosmic horizon. If our universe is one mathematical structure, then the realm beyond it is not a higher dimensional bulk or a sea of inflationary energy. It is the entirety of the mathematical landscape. Every possible mathematical structure that is logically consistent exists in a physical sense. This is the ultimate multiverse, a cosmos of infinite diversity, not governed by the whims of quantum fluctuations or colliding branes, but by the immutable rules of logic and computation. In this vast mathematical multiverse, our specific universe, with its 4 dimensions and its particular set of fundamental particles and forces, is just one entry in an infinite catalog. There are mathematical structures that describe universes with 5 spatial dimensions, where creatures navigate directions we cannot conceive. There are structures where the number pi has a different value, where the Pythagorean theorem is false, and where the very concept of geometry is alien to our own. Some of these structures would describe barren, empty spaces. Others would be teeming with complexity far beyond our own. The implications of this are as profound as they are disorienting. First, it offers a potential solution to the great mystery of why mathematics is so unreasonably effective in describing the natural world. The physicist Eugene Wigner once famously pondered this, questioning why math, a product of human reason, should so perfectly mirror the behavior of the physical cosmos. The mathematical universe hypothesis provides a blunt answer. It's because the physical cosmos is mathematics. We are not discovering pre-existing physical laws and then finding the math to match. We are slowly deciphering the properties of the specific mathematical structure we are embedded within. Our physics is just the applied mathematics of our particular cosmic address. Secondly, this hypothesis completely redefines the concepts of existence and reality. In this framework, there is no distinction between the abstract and the physical. A universe described by a beautiful, self-consistent set of equations doesn't just exist as an idea in a mathematician's notebook. It exists as a physical reality somewhere in the mathematical multiverse. This means that every conceivable universe that is not logically impossible is real. Every variation of the laws of physics, every alternate history, every fantastical world you could imagine, if it can be described by a coherent mathematical structure, it exists. Our own sense of being, our consciousness, is then an emergent property of the particular complex computational structure that is our space-time. We are not biological beings in a physical world. We are self-aware patterns within a grand cosmic equation, discovering the very rules that define our own existence. But if our universe was born from the ravenous heart of a black hole in a parent cosmos, what does that say about the world outside our own? This is the crux of black hole cosmology, a theory that paints a breathtakingly fractal picture of existence. In this view, the outside of our universe is simply the universe from which our black hole progenitor formed. We are on the inside of an event horizon, looking inwards at our own cosmic expanse, while the parent universe carries on, largely oblivious to the entire new reality that has been birthed within one of its darkest objects. The fundamental forces and constants that govern our reality, from the speed of light to the mass of an electron, would not be arbitrary. They would be inherited, shaped by the specific conditions of our black hole's collapse and the physics of the parent universe. This offers a potential and deeply elegant explanation for the fine-tuning we observe. Perhaps only black holes that form with a very specific set of parameters can spawn large, stable, long-lived universes capable of fostering complexity and life. We may live in a universe that is finely tuned simply because it is the product of a very specific and successful type of cosmic reproduction. This fractal nesting of universes within black holes also provides a stunningly simple answer to the age-old question of what came before the Big Bang. The answer is another universe operating under a similar but not necessarily identical set of physical laws. Our Big Bang was not the absolute beginning of time and space, but a transitional event. the moment a region of a parent universe collapsed into a black hole and pinched off into its own separate space-time continuum. And by extension, many of the black holes that form within our own cosmos, the stellar mass ones scattered throughout galaxies and the supermassive giants at the centers, could themselves be cosmic wombs. Each one could contain, within its hidden singularity, the seed of an entire new universe bubbling into existence in its own disconnected spacetime. Our cosmos would then be both a daughter and a potential mother, a single branch on an infinite growing tree of realities, a cosmic Russian doll where every dark heart contains the potential for a new dawn. While the cyclical model of colliding branes offers one vision of cosmic rebirth, another truly extraordinary idea comes from one of the most brilliant minds in theoretical physics, Sir Roger Penrose. His theory, known as conformal cyclic cosmology, presents a universe without beginning or end, but its mechanism is entirely different and hinges on a profound and beautiful symmetry in the laws of physics. Penrose proposes that the distant future of our universe and the hot, dense birth of the next are, in a very specific mathematical sense, the same thing. The end is literally the beginning. To understand how this is possible, we need to follow the cosmic timeline to its absolute extreme. Billions of years from now, all the stars will have burned out, their ashes scattered. Galaxies will have evaporated as their stars either die or get ejected into the intergalactic void. Supermassive black holes, the last bastions of structure, will slowly evaporate away via Hawking radiation over timescales so vast they defy imagination. What remains is a universe that is almost perfectly empty, cold, and dark. It contains only an incredibly diffuse sea of leftover photons and fundamental particles like electrons and positrons, all so spread out that they almost never interact. In this final state, the universe has expanded to such a staggering degree that it has effectively lost all sense of scale. There are no rulers left to measure distance, no clocks left to tick off time. A single, lonely photon could travel for an eternity without ever encountering another particle. This is where Penrose's genius insight comes into play. He realized that in such a smooth, empty, and featureless state, the universe undergoes a profound transformation. It becomes what is known as conformally invariant. This is a complex mathematical concept, but the core idea is about losing any absolute sense of distance or duration while preserving angles. Imagine a detailed map of the world. You can shrink that map down to the size of a postage stamp or blow it up to cover a football field. The shapes of the continents and the angles between the lines of longitude and latitude remain the same, but the scale is completely different. In a conformally invariant universe, the concepts of big and small, or a long time versus a short time, cease to have any absolute meaning. The entire, vast, cold, and ancient cosmos of the far future becomes mathematically identical to a tiny, hot, and dense point. And what is a tiny, hot, and dense point? It is the Big Bang. In the framework of conformal cyclic cosmology, the infinite expansion and cooling of one eon, Penrose's term for a universe cycle, smoothly and seamlessly connects to the explosive hot beginning of the next. The cold, vast emptiness of the future becomes the hot, dense singularity of a new creation. There is no magical bounce, no violent collision. There is simply a rescaling, a reset of the cosmic clock where the end state of one era provides the initial conditions for the next. The universe forgets its scale and in doing so is reborn. One of the most compelling and testable aspects of Penrose's theory involves a cosmic fossil left over from the previous eon. He suggests that extremely high-energy events from the universe before ours, like the collisions of supermassive black holes, could have left faint imprints on our own cosmic microwave background radiation. These imprints would manifest as concentric circles of slightly varying temperature, known as Hawking points. The search for these circles in the data from satellites like the Planck Observatory has been a subject of intense debate and investigation. While the evidence is not yet conclusive, the very fact that this elegant, almost philosophical idea makes a concrete, falsifiable prediction shows its power as a serious scientific proposal, not just a flight of fancy. What does this mean for our place in the cosmos? In the vision of conformal cyclic cosmology, our universe is not a one-off experiment. It is one frame in an infinite cosmic film, a single eon in an endless sequence. Every galaxy, every star, every living creature is a temporary pattern that emerges, flourishes, and vanishes within its own cycle. But the underlying process, the great conformal symmetry that links the death of one world to the birth of the next, is eternal. It is a vision of the cosmos as a phoenix, forever rising from its own ashes, not through fire and violence, but through the serene and silent mathematics of infinite space and timeless symmetry. Yet, for all the grandeur of these cosmic cycles and mathematical structures, one of the most unsettling ideas in all of physics isn't a theory about what lies beyond, but a terrifying implication that arises from some of the very models we've been exploring. This is the Boltzmann brane paradox, a thought experiment that uses the logic of probability to launch a direct assault on our confidence in reality itself. The story begins in the 19th century with the physicist Ludwig Boltzmann, who helped develop the foundations of statistical mechanics. He was grappling with a profound question: why does time seem to move in one direction from order to disorder when the underlying laws of physics are largely time-symmetric? His work introduced the concept of entropy, a measure of disorder in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time, which gives us the arrow of time we experience. A cup of hot coffee cools down to room temperature. It never spontaneously heats up. A shattered vase does not reassemble itself. But Boltzmann made a crucial and deeply strange observation. In a truly infinite or eternal universe that has reached a state of maximum entropy, a featureless, lukewarm soup of particles in equilibrium, random fluctuations are not just possible, they are inevitable. Given enough time, the random jostling of particles will, by pure chance, create pockets of order out of the chaos. Most of these fluctuations would be small and short-lived. But in a cosmos with infinite time and space, even the most astronomically improbable events are not just likely, they are guaranteed to happen an infinite number of times. A collection of atoms could randomly assemble into a perfect, brand new rose. Another fluctuation could spontaneously form a fully functioning laptop computer. And in the most extreme scenario, a random quantum fluctuation could, against unimaginable odds, spontaneously conjure into existence a fully formed, self-aware human brain, complete with a lifetime of detailed, coherent but entirely false memories. This is the nightmare of the Boltzmann brane. This disembodied consciousness would flicker into existence for just a moment, believing itself to be a real person with a real past, perhaps remembering a childhood, a career, the feeling of sunlight on its face, only to almost instantly dissolve back into the random chaos from which it came. Its entire perceived reality would be a fleeting, accidental mirage. Now, here is the probabilistic trap. In an eternal, high-entropy multiverse, the spontaneous, random fluctuation of a single, self-aware brain is vastly more probable than the slow, painstaking, and highly ordered process of cosmic evolution that led to our universe, our galaxy, our planet, and the 14-billion-year chain of biological events that produced you and me. The formation of a single brain is a simple, low-entropy event compared to the creation of an entire, structured cosmos. Therefore, if such a multiverse exists, the overwhelming statistical probability is that any given conscious observer, including you right now, is far more likely to be one of these fleeting Boltzmann brains than a product of a long, coherent cosmic history. This paradox forces us to question the very nature of our own existence and the reliability of our memories and observations. How can you be certain that the world you remember is real? Your conviction that you were born, that you learned about the Big Bang in school, that you are watching this video right now, all of this could be nothing more than a set of data points randomly generated in a disembodied mind that came into being mere moments ago. The universe you think you see around you could be a complete hallucination, a detailed but false memory implanted at the moment of your spontaneous creation. This isn't just a philosophical curiosity. It presents a direct challenge to cosmological theories that predict an eternal or infinite future. If a theory logically implies that Boltzmann brains should outnumber ordinary observers like us by an infinite ratio, then that theory has a serious problem, because our very existence as seemingly stable, long-lasting observers provides evidence against it. Physicists are therefore forced to either find flaws in the theories that lead to this conclusion, or find a way to show why our ordered experience is more likely, a puzzle that remains at the bleeding edge of cosmology and the philosophy of science. From the unsettling probability of being a fleeting Boltzmann brain, we turn to a theory that offers an even more humbling origin story for everything we know. This is the idea that our entire universe, in all its magnificent complexity, is nothing more than a random blip, a momentary hiccup in an infinite and eternal sea of absolute nothingness. The theory of the universe as a quantum fluctuation proposes that we are the ultimate free lunch, a cosmic accident of such staggering improbability that it challenges our very notion of what it means to exist. To understand how something can come from nothing, we first have to redefine what we mean by nothing. In our everyday experience, nothing is just empty space, a complete void. But in the world of quantum mechanics, as described by quantum field theory, there is no such thing as a true, perfect vacuum. What we call empty space is actually a seething, bubbling cauldron of activity. At the tiniest scales, the fabric of reality is constantly in flux. Virtual particle-antiparticle pairs spontaneously pop into existence, borrowing energy from the vacuum for an unimaginably brief moment before annihilating each other and vanishing back into the void. This isn't just a theoretical idea. It's a verified phenomenon with real-world effects, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum are gently pushed together by the pressure of these virtual particles flickering in and out of being all around them. So the quantum void is not empty and passive. It is a dynamic arena where something and nothing are in a constant, frenetic dance. Now, take this quantum quirk and extrapolate it to the most extreme scale imaginable. If the quantum vacuum can spontaneously generate a pair of particles for a fleeting instant, could it not, by some unimaginably rare statistical fluke, generate something vastly larger? The mathematics of quantum theory does not forbid it. In an eternal void, given an infinite amount of time, every possible fluctuation, no matter how improbable, is not just possible but inevitable. Our universe, in this view, is simply the rarest of all possible quantum fluctuations, a colossal, sustained burst of energy and matter that, against all odds, did not immediately collapse back into nothingness. Instead, it found a stable enough configuration to undergo inflation, expand, cool, and eventually give rise to galaxies, stars, planets, and us. We are not the product of a grand design or a cyclical rebirth, but a single, spectacular statistical outlier in an endless cosmic silence. This leads to a truly profound implication for what lies outside our universe. If this theory is correct, then there is no outside in the sense of other universes or higher dimensions. The true, fundamental reality is the stable, eternal vacuum state, the ultimate nothing from which we temporarily emerged. This primordial void is the baseline of existence, a state of zero energy and infinite stability. Our universe is just a localized bubble of excited, higher energy vacuum that is exceptionally long-lived. From the perspective of this eternal nothing, our 14 billion-year cosmic history is less than a blink of an eye, a fleeting dream in an endless night. All of space and time, every moment of joy and sorrow, every triumph of life and civilization is contained within this transient quantum event. When the fluctuation eventually subsides, perhaps when the last black hole evaporates and all matter decays, our universe will simply wink out of existence, its energy debt repaid, leaving no trace in the infinite, featureless void from which it came. We are living on borrowed time and borrowed energy, a magnificent but temporary anomaly in an ocean of tranquil nothingness. But to flip the concept of a black hole completely on its head, we must now venture into one of the most speculative and fascinating ideas in all of theoretical physics, the white hole. If a black hole is a cosmic one-way street where matter and energy can fall in but nothing, not even light, can ever escape, then a white hole is its theoretical antithesis, a region of space-time where matter and energy can only pour out and nothing can ever enter. It is a cosmic fountain of existence, a gushing spring in the fabric of reality that continuously expels without ever consuming. While we have overwhelming observational evidence for black holes, a white hole has never been detected, and many physicists argue they may be mathematically possible but physically forbidden by the laws of thermodynamics. Yet their conceptual power is undeniable, and they lead to one of the most elegant and mind-bending proposals for our universe's origin, that our entire cosmic genesis, the Big Bang, was not a singularity in time but the violent eruption of a white hole. Think of the connection between a black hole and a white hole not as two separate objects, but as two ends of a single cosmic tunnel, a wormhole, or as it is known in the equations of general relativity, an Einstein-Rosen bridge. According to this classic solution, if you were to fall into a black hole, the mathematical description of your journey doesn't end at the crushing singularity. Instead, the equations suggest your path would continue through a short-lived tunnel, a throat of distorted space-time, and you would be ejected out of the other end through a white hole into a completely different region of the cosmos. In this pristine mathematical picture, the black hole is the entrance and the white hole is the exit. The problem is, this elegant bridge is incredibly unstable. It would pinch off and collapse faster than any particle or piece of information could possibly traverse it, preventing any practical travel. But if we suspend the practicalities and focus on the raw geometry, it paints a stunning picture. A black hole in one universe could be physically connected to a white hole in another. This is where the idea becomes truly cosmic in scale. What if the Big Bang itself was the white hole end of such a tunnel? Imagine a massive star in a vast parent universe collapsing at the end of its life. It forms a black hole, its event horizon sealing off a region of space-time from the rest of its native cosmos. But on the other side of that event horizon, from the perspective of the space inside the newborn black hole, the event horizon isn't a point of no return, it's a point of no entry. It is a boundary from which all the matter and energy that originally collapsed is now explosively reborn. From the inside, this looks like a sudden, hot, and incredibly dense beginning. It looks, for all intents and purposes, exactly like a Big Bang. In this breathtaking scenario, our entire universe, from the first instant of time to the farthest galaxy, exists inside the black hole that formed in that parent cosmos. What we perceive as our entire cosmic expanse is, from the outside perspective, the hidden interior of a singularity. The Big Bang was the moment that white hole began spewing forth the transformed remains of a star, or perhaps an entire galaxy, that fell into the black hole on the other side. This radical perspective offers a profound shift in our understanding of inside and outside. We, living within this universe, are on the inside of the black hole, looking outwards towards our own cosmic horizon. But from the vantage point of the parent universe, our entire reality is locked away behind an impenetrable event horizon. They cannot see us and we cannot see them. The connection, the wormhole throat, likely severed moments after the white hole's eruption, leaving our universe as a self-contained, isolated bubble of space-time. This creates a stunning form of cosmic reproduction, where black holes act as seeds for new universes. Every time a black hole forms in a parent cosmos, it may give birth to an entirely new baby universe in its interior, with its own laws of physics and its own cosmic destiny. Our universe, then, is not the first and only one, but rather one branch on an infinite, growing tree of realities, each born from the gravitational collapse of a massive object in a pre-existing world. The implications of this white hole cosmology extend even further, potentially offering a fresh perspective on the nagging mystery of cosmic fine-tuning. Why do the fundamental constants of nature seem so perfectly calibrated to allow for the existence of complex structures and life? If our universe was born from a black hole in a parent cosmos, then the laws of physics we inherited may not be random. They could be the specific, transformed parameters of the matter that underwent that initial collapse. The process of gravitational implosion and white hole explosion might act as a cosmic filter, selecting for only certain stable configurations that can produce large, long-lived universes like our own. We don't live in a specially designed cosmos. We live in one that was successfully bred from a previous one, a universe with the right genetic code of physical laws to foster galaxies, stars, and ultimately, inquisitive minds to ponder its own incredible origin. The ekpyrotic universe takes the breathtaking vision of the brane world and sets it in motion, transforming a static multiverse into a dynamic, rhythmic engine of cosmic rebirth. To truly grasp this idea, picture our three-dimensional universe not as an island, but as one of two vast parallel membranes, like two immense floating sheets of paper separated by a tiny gap in a higher dimensional space called the bulk. For most of the cycle, these two branes are drawn slowly together by an invisible force, perhaps a kind of spring-like tension in the bulk itself. This approach is not a head-on crash, but a gradual, elegant convergence over trillions of years. Then they meet. The collision is not a destructive impact in the conventional sense, but a transformative event of pure, unadulterated energy. From our perspective, trapped within our brain, this collision would manifest as a sudden, universe-wide injection of heat and radiation, a cataclysmic flash that looks, for all intents and purposes, exactly like the hot, dense state we call the Big Bang. In this model, the Big Bang was not the beginning of time, but a pivotal turn in an endless cosmic cycle, a moment of renewal where the universe is violently reheated and refilled with the raw materials for a new cosmic era. This process elegantly solves several of the most stubborn puzzles left by the standard Big Bang theory. One of the biggest mysteries is why our universe is so remarkably flat and uniform on large scales. The ekpyrotic scenario provides a natural explanation. During the long, slow approach of the two branes, any wrinkles or irregularities in their structure are gently stretched and smoothed out. Think of it like slowly pulling a rumpled tablecloth taut before setting it for a meal. By the time the branes collide, their surfaces are incredibly flat and uniform. This inherited smoothness then becomes the initial condition for our new cosmic cycle, explaining why we observe such a homogeneous cosmos today without needing a period of hyper-fast inflation. The tiny quantum fluctuations that were present during the approach get imprinted onto the new universe as well, providing the microscopic seeds that will later grow over billions of years into the vast cosmic web of galaxies and galaxy clusters we see mapping the sky. What follows the collision is the cosmic drama we are familiar with. The branes bounce apart and our universe enters a long period of expansion and cooling. Matter and radiation from the fiery collision begin to coalesce, forming the first protons and neutrons, then atoms, and eventually stars and galaxies. Life emerges on worlds like ours, and civilizations rise to look up at the night sky and wonder about their origins. But the cycle is not complete. After the expansion slows, the invisible force in the bulk begins to draw the branes together once more. The universe contracts not in a chaotic crunch but in a controlled, smooth reversal. galaxies are pulled closer together, the cosmic background radiation heats up, and all structures are eventually broken down and homogenized, preparing the stage for the next great collision. This endless, timeless dance of creation, approach, collision, expansion, and contraction suggests a cosmos without true beginning or end, a perpetual motion machine of reality where every ending is merely a prelude to a new beginning, and every Big Bang is an echo of a previous embrace in the higher dimensional dark. Building directly on the simulation idea, there exists an even more fundamental proposal that doesn't just suggest our universe is like a computer, but that it literally is one. This is the theory of digital physics, or the computational universe, a paradigm that posits the very fabric of reality is made of information, and that the dance of particles and forces we observe is the output of a cosmic computation running on the substrate of spacetime itself. The pioneers of this view, like Konrad Zuse and Edward Fredkin, proposed that the universe isn't merely conveniently described by mathematics. It is a giant, discrete-state cellular automaton, a cosmic grid where every tiny piece of spacetime is a cell that updates its state based on a set of simple, underlying rules. In this view, an electron isn't a tiny, solid ball orbiting a nucleus. It is a persistent pattern of information, a specific configuration of bits in the cosmic lattice that evolves according to the universe's fundamental algorithm. The laws of physics, then, are not mysterious, pre-existing commandments, but are simply the emergent properties of this ongoing computation. Gravity, electromagnetism, and even the flow of time itself are the high-level consequences of countless tiny, digital operations happening at the most basic level of reality. This computational framework provides a beautifully elegant explanation for some of the deepest mysteries in physics. Take the aforementioned graininess of the universe, the fact that there appears to be a smallest possible unit of space, the Planck length, and a smallest possible unit of time, the Planck time. In a continuous, analog universe, this fundamental limit is puzzling. But in a digital, computational universe, it is exactly what you would expect. Every computer has a finite resolution and a clock speed. The Planck scale represents the native pixel size and processing cycle of the cosmic computer. Reality isn't rendered in infinitely smooth curves. It is computed in discrete, tiny steps. Furthermore, the conservation laws that govern physics, the fact that energy and momentum can neither be created nor destroyed, find a natural parallel in the world of computation. In a deterministic computer program, information is conserved. It can be transformed and moved around, but it is never truly lost. The unbreakable conservation laws of our universe could be a direct reflection of this underlying principle of information preservation at the computational level. This perspective radically reshapes the question of what lies beyond our cosmic horizon. If our universe is a computation, then beyond the observable universe isn't a physical place filled with more galaxies or other branes. Instead, it is the boundary of the computational resource allocated to our particular simulation or reality. We are living inside a running process, and the edge of our universe might be the literal edge of the processing volume. This leads to two profound and equally mind-bending possibilities for what exists outside this boundary. The first is that we are in a simulated reality, and what lies beyond is the physical hardware of the simulating civilization, their world, which we would have to call the base reality. In this scenario, the programmer is not a metaphorical figure but an actual entity, a being or a society of beings whose technology is so advanced that they can instantiate an entire cosmos as a program on their machinery. Their motivations are completely inscrutable to us. We could be an archaeological simulation, a grand experiment in sociology, a work of art, or even just a screensaver in a post-human child's bedroom. Our struggles, our joys, our entire history would be data points in their project. The second possibility is even stranger, removing the need for an external programmer altogether. This is the concept of the universe as a self-executing mathematical structure, a computation that simply is. In this view, the cosmos doesn't require a machine to run on. Existence and computation are one and the same. What lies beyond our universe, then, is not a higher reality but simply more of the computational lattice in an uncomputed potential state. The laws of physics that govern our region are the specific, self-consistent algorithm that is currently executing. But outside our horizon, the lattice might be running different algorithms, manifesting as universes with completely different physical laws. This creates a natural, digital multiverse, not of bubbling, inflating domains, but of adjacent computational domains processing different sets of rules. We are not a program running on someone else's computer. We are one expression of a vast, perhaps infinite, computational cosmos where every possible program that is logically consistent is running somewhere. In this digital metaphysics, the very concepts of inside and outside become questions of memory allocation and processing boundaries rather than physical location, suggesting that the ultimate nature of reality is not substance but syntax. While the many worlds interpretation offers a dizzying vision of reality endlessly branching, another equally profound idea suggests the splitting isn't happening out in the cosmos but right inside our own mind. This is the many minds interpretation, a quantum theory that places the bewildering nature of reality not in the fabric of space-time, but in the fabric of consciousness itself. It begins with the same bizarre quantum premise. A particle exists in a blurry cloud of all possible states, a superposition, until it is observed. The classic Schrödinger's cat thought experiment highlights this perfectly. The cat in the box is both alive and dead simultaneously until someone looks inside. The standard many worlds theory resolves this by saying the universe splits in two, creating one world with a live cat and another with a dead one. The many minds interpretation, however, proposes a radically different solution. It suggests the universe never splits at all. Instead, the entire cosmos, including the cat, remains in a single, vast, and unified quantum superposition. The splitting happens within the consciousness of the observer. In this view, your mind does not simply perceive a single, predetermined reality. At the moment of observation, your conscious awareness itself splits into multiple, separate streams. One stream of your consciousness perceives the cat as alive, while another, completely separate stream of your consciousness perceives the cat as dead. Both outcomes are equally real, but they are experienced by different versions of your mind, all while your physical body and the entire universe remain singular and undivided. You are not one person witnessing one reality. You are a multitude of minds, each tracing its own unique path through the infinite tapestry of possible experiences contained within the one true, universal quantum state. The feeling of being a single, continuous self is an illusion, a trick of memory where only one thread of your consciousness is active at any given moment, unaware of its countless counterparts. This leads to a staggering redefinition of what constitutes the world beyond our universe. If the many minds interpretation is correct, then the true nature of reality beyond our perceived world is not a collection of other physical universes, but the immense, unobserved quantum superposition itself. This is the foundational layer of existence, a realm where every possible event, every potential outcome, and every cosmic history coexist simultaneously in a state of pure potential. What we think of as our singular, concrete reality is merely the narrow slice of this superposition that our current stream of consciousness has selectively latched onto. The world outside your window, with its specific arrangement of clouds and cars, is just one thread being followed by your mind. At this very moment, alternative versions of your mind are perceiving different clouds, a different car in the driveway, or even an entirely different life. The beyond is not a place you can travel to. It is the ocean of unlived possibilities in which our lived experience is but a single, fleeting current. The implications of this for our understanding of self and identity are deeply unsettling. It challenges the most fundamental assumption we have, that we are a unified person moving through a single timeline. In the many minds picture, there is no single you. There is a branching tree of conscious experiences, all stemming from the same origin point but forever diverging. The version of you that decided to watch this video is having one experience, while another version, in the same room and the same body, decided to do something else and is having a completely different experience. Both are real and both are you, yet they are utterly isolated from one another. Your sense of making a choice is an illusion. Every possible choice is made, and a different mind is created to experience the consequences. This transforms life from a linear narrative into a sprawling, simultaneous exploration of every conceivable path, with your central identity being less a captain and more a leaf caught in an infinite river of possibilities. When we connect this back to our original quest, what lies beyond the cosmic horizon, the many minds interpretation offers a uniquely introspective answer. The ultimate frontier may not be an external boundary in space, but an internal boundary of perception. The universe does not need to be physically infinite to contain all possibilities. It only needs to be quantum mechanically complete. The entire cosmic history, from the Big Bang to the formation of galaxies to the rise of life on Earth, exists in a grand superposition. Our stream of consciousness is simply one of countless ways to navigate this single, magnificent quantum reality. The edge of the observable universe is just another feature within this superposition, and what lies beyond it from our perspective is simply one of the many possibilities our mind has not yet actualized. In the grandest sense, the final frontier is not out there among the stars, but within the silent, vast depths of a conscious awareness that is far more vast and fragmented than we ever dared to believe. But if your mind is reeling from the possibilities of fractured consciousness and branching realities, prepare for a theory that offers a strange kind of comfort in its infinite repetition. We now travel back to a classic model of the cosmos, the static universe, and give it a modern, dizzying twist. This concept, known as the eternal return, proposes a cosmos that is not only infinite in space but eternal in time. And within that boundless arena, the implications for our own existence become simultaneously awe-inspiring and humbling. The idea of a static, unchanging universe was once a popular alternative to the Big Bang theory. In this steady-state model, the cosmos had no beginning and will have no end. It simply exists, always has, and always will, with new matter slowly being created to fill the gaps as old galaxies drift apart, maintaining a constant average density. While this model has largely been supplanted by the evidence for the Big Bang and cosmic expansion, its philosophical core, a universe without a definitive start or finish, combines with the principles of statistics to produce one of the most staggering ideas in all of cosmology. In a truly infinite and eternal universe, every single possible event that can happen must happen, not just once but an infinite number of times. To understand why, consider a simple analogy: a deck of cards. There are a finite number of ways to shuffle a standard 52-card deck. If you were to shuffle that deck continuously for an eternity, you would eventually, by pure chance, produce the exact same sequence of cards again. Now scale this up to a cosmic level. The universe is made of a finite number of particles: protons, neutrons, electrons, arranged in a finite number of possible configurations governed by the laws of physics. In an infinite expanse of space and time, the number of possible arrangements, while astronomically large, is still finite. Therefore, given enough time and enough space, every single possible arrangement of matter must occur. And once it occurs, it must occur again and again and again forever. There is no unique event. Every sunrise, every falling leaf, every conversation has already happened countless times in the past and will happen countless times in the future. This is where the concept becomes deeply personal. It means that somewhere out there in the vastness, at this very moment, there is not just one of you watching this video. There are an infinite number of identical copies of you, sitting in an identical room on an identical planet, orbiting an identical star in an identical galaxy. Each copy has the exact same memories, the same thoughts, and the same life history, but the repetition does not stop with you. It extends to every detail of our world. There is an infinite number of perfect copies of Earth, with every mountain range, every ocean current, and every city street arranged in precisely the same way. Our entire Milky Way galaxy, with its 400 billion stars and its specific spiral arm structure, is duplicated an infinite number of times across the cosmos. In this view, the question of what lies beyond our observable horizon receives a simple yet utterly profound answer: more of the same. More galaxies, more stars, more planets, and ultimately, more copies of everything we know, arranged in an endless fractal pattern of repetition. This notion of the eternal return forces us to confront the nature of identity and chance on a scale that defies human intuition. Your life, with all its unique joys and sorrows, its specific triumphs and failures, is not a one-of-a-kind story. It is a template, a pattern that the universe is bound to replicate over and over. The version of you that exists right now is just one instance in an infinite series. Some of these copies will have futures that diverge from this exact moment based on quantum fluctuations. Perhaps in one, a different video is recommended next, while in another, a phone rings, interrupting the viewing. But for an infinite number of them, the future will unfold in lockstep with your own, every decision and every event mirrored perfectly. This transforms our understanding of self from a singular entity into a statistical inevitability, a pattern that the cosmos is compelled to express, not out of purpose, but out of the cold, impersonal logic of infinite probability. And what does this mean for the ultimate fate and structure of everything? It suggests a cosmos that is not evolving toward a unique conclusion, but is instead engaged in an eternal, cyclical reconfiguration of all possible states. There is no final heat death or big crunch that ends the story, because the story has no end. Instead, the universe is a perpetual kaleidoscope where every possible arrangement of matter, from the most orderly to the most chaotic, is perpetually coming into and out of existence across infinite space and time. The grand cosmic drama of galaxy formation, star birth, and life's emergence is not a one-act play with a beginning, middle, and end. It is an infinite repertoire of performances, each identical in script but separated by unimaginable gulfs of space, all playing out simultaneously on the endless stage of a static, eternal reality. In this vision, to search for what lies beyond is not to seek something new or different, but to confront the ultimate conclusion that every possible reality, including our own, is not just out there, but is everywhere forever. But to truly grasp the nature of a higher dimensional reality, we have to step down a dimension and visit a fictional world that has become a cornerstone of scientific thought. Imagine a universe that is completely flat, a two-dimensional plane like a sheet of paper. This is the world of flatland, a concept introduced by Edwin Abbott in the 19th century. In flatland, its inhabitants are geometric shapes, triangles, squares, circles who can only move left, right, forward, and backward. They have no concept of up or down. Their entire reality exists on that single flat surface. Now picture what happens when a three-dimensional object like a sphere passes through flatland. From the perspective of the two-dimensional beings, the event is utterly baffling. They would not see a sphere. Instead, they would witness a single point that suddenly appears out of nowhere. That point then grows into a small circle, which expands to a maximum diameter as the sphere's equator passes through their plane, and then shrinks back down to a point before vanishing completely. For the Flatlanders, this is a magical, impossible event. They cannot comprehend the true, three-dimensional nature of the sphere. They can only perceive its two-dimensional cross-sections. Their entire scientific understanding would be based on these mysterious appearing and disappearing circles, with no framework to explain the fuller reality that exists just above them. We are the Flatlanders. Our universe appears to us to have 3 dimensions of space and 1 of time. But what if that is an illusion of our limited perception? What if our entire cosmos is just a 3-dimensional brane, a membrane floating in a higher dimensional space, just like Flatland is a 2-dimensional sheet? From this perspective, a being from a 4-dimensional spatial reality would perceive our universe in a way that would seem like pure magic to us. They could look down upon our 3-dimensional world and see everything all at once. They could peer directly into the center of a sealed sphere, examine the interior of your body without making an incision, and observe every room in every building on Earth simultaneously, as if our walls were no more substantial than lines drawn on paper. For such a being, the concepts of inside and outside would be rendered meaningless. They could effortlessly remove an object from a locked safe without ever touching the door, simply by moving it through the 4th spatial dimension, a direction that is completely inaccessible and unimaginable to us. This higher dimensional framework isn't just a philosophical curiosity. It provides a powerful potential explanation for some of the most stubborn mysteries in modern physics. Take dark matter, for instance. We know galaxies rotate so fast that they should fly apart, yet something invisible provides the extra gravitational glue to hold them together. In our 3-dimensional view, we postulate the existence of an unseen form of matter, but from a higher dimensional perspective, the explanation could be radically different. The gravity we feel in our 3-dimensional brain might not be confined to it. Just as the Flatlanders could only see a slice of the sphere, the gravitational force from matter in our universe could be leaking out into the extra dimensions. This dilution would make gravity appear weaker on our brain than it truly is in the full, higher dimensional reality. What we interpret as missing mass causing extra gravity could, in fact, be the signature of gravity's true strength bleeding into dimensions we cannot see. The effects of dark matter might not be caused by a mysterious particle at all, but could be an artifact, a shadow, of the true nature of gravity operating in a cosmos with more than 3 spatial dimensions. Another profound puzzle that might find its solution in higher dimensions is the bizarre phenomenon of quantum entanglement, which Einstein famously called spooky action at a distance. This is where 2 particles become linked, and no matter how far apart they are separated, measuring the state of one instantly determines the state of the other. This seems to violate the cosmic speed limit set by the speed of light, but if our universe is embedded in a higher dimension, this spookiness might vanish. Imagine 2 points on a vast 2-dimensional piece of paper that are a foot apart. For a Flatlander confined to the paper, traveling between them is a long journey. But for a 3-dimensional being, the distance is trivial. They could simply fold the paper in the 3rd dimension, bringing the 2 points into direct contact. In an analogous way, 2 entangled particles in our 3-dimensional space might only appear to be far apart. In the higher dimensional bulk, they could be virtually touching, connected by a shortcut through a dimension we cannot perceive. Their instant connection isn't a signal traveling faster than light through our space. It's a reflection of a deeper, more intimate connection through the larger architecture of reality. What we see as a mysterious, non-local link could be a perfectly local interaction viewed from the higher dimensional canvas upon which our universe is painted. After exploring a cosmos teeming with endless copies and higher dimensions, we must now confront perhaps the most formidable and conceptually challenging theory of all. This is the nulliverse, the profound and unsettling proposal that beyond the cosmic horizon there is precisely nothing. Not empty space, not a dark void, but an absolute and total absence of everything. No space, no time, no matter, no energy, and not even the potential for such things to exist. The human mind evolved to navigate a world full of objects and events, hits a fundamental wall when trying to grasp this concept. When we try to picture nothing, we inevitably imagine something, a vast, dark, empty room or the blackness of deep space. But these are all stages within a theater of existence. True nothingness is the absence of the theater itself. It is not a black canvas, it is the absence of the concept of a canvas and the absence of anyone to perceive it. The nulliverse suggests that the universe isn't an object floating in a larger container. It is all there is, and at its boundary, existence itself simply stops. This idea forces us to question the very language we use to frame our inquiry. When we ask what lies outside the universe, we are making a subtle but critical assumption. The word outside is a spatial term. It implies a container, a larger arena in which our universe resides. But if space and time are properties of our universe born in the Big Bang, then the concept of an outside becomes a logical error, a category mistake. It's like asking what is north of the North Pole. The question uses a directional term from a system that ceases to be applicable at that boundary. In the same way, outside is a concept that only has meaning within the context of our spatial continuum. To apply it to the totality of existence is to misuse the word, projecting the rules of our local reality onto a context where those rules no longer hold. The edge of the universe may not be a place you can travel to or look past. It may be the ultimate end of all places, where the very ideas of where and when dissolve into incoherence. Philosophers have grappled with this chasm in our understanding for centuries. The difficulty is that our consciousness seems hardwired to operate within a framework of subject and object, of things existing in relation to other things. We can contemplate the absence of any particular thing, but contemplating the absence of all things, including the framework for things, is a feat of mental abstraction that feels almost like trying to lift ourselves by our own bootstraps. Some thinkers argue that true nothingness might not just be difficult to imagine, but could be logically impossible because the moment you define it or conceive of it, you have created a something, the concept itself. The nulliverse, then, is not a void waiting to be explored, but the total negation of the conditions required for exploration, thought, or even the word is to have any meaning. It is the ultimate answer to our question, but an answer that collapses the question itself into silence. Now we arrive at a theory that stands apart from all the others, not by proposing a new kind of cosmos, but by placing you, the observer, at the very center of creation itself. This is the participatory anthropic principle, a mind-bending concept pioneered by the brilliant physicist John Archibald Wheeler. It proposes a role for consciousness so profound that it challenges the bedrock of our reality, the idea that the past is a fixed and unchangeable record. Wheeler's radical suggestion is that the universe only truly comes into existence in a concrete sense when it is observed by a conscious being. In this view, we are not mere passengers in a pre-existing cosmos. We are active participants in its ongoing creation, and our act of looking back in time is what sculpts the very history we believe we are discovering. To grasp the sheer audacity of this, we need to return to the quantum realm and its infamous observer effect. In the classic double-slit experiment, a single particle like an electron is fired at a barrier with two slits. If no one is watching which slit it goes through, the particle behaves like a wave, passing through both slits simultaneously and creating an interference pattern on the detector behind. It exists in a blurry state of all possible paths, but the moment you place a measuring device to determine which slit the electron actually used, this wave-like behavior vanishes. The particle instantly chooses a single, definite path, and the interference pattern disappears. The act of observation, of measurement, seems to force the particle to collapse from a spread-out cloud of potential into one specific, localized reality. Wheeler took this quantum weirdness and scaled it up to a cosmic level in his famous delayed choice thought experiment. Imagine light from a distant quasar billions of light years away is bent by a gravitational lens, creating two paths around a galaxy before arriving at our telescope on Earth. We can choose to set up our detector to see which path an individual photon took, and it will obediently act like a particle having taken one specific route. Or we can choose an apparatus that allows the photon to interfere with itself, proving it took both paths like a wave. The staggering implication is this: our choice of measurement today seems to determine what that photon did billions of years ago, back when the dinosaurs roamed the Earth. The past, in a very real sense, is not settled until it is observed in the present. This is where the participatory anthropic principle weaves together quantum mechanics with our own existence. The standard anthropic principle simply notes that the universe's constants are fine-tuned for life, and since we are here to observe it, we necessarily find ourselves in a universe capable of supporting us. It's a passive statement. Wheeler's participatory version is active and far more profound. It suggests that the universe has remained in a hazy, unrealized state of quantum potential for billions of years, a vast collection of possibilities waiting for a specific outcome. The emergence of conscious life is not a lucky accident in a ready-made world, but the very trigger that forces the cosmos to make concrete choices about its own history, solidifying a timeline that leads inevitably to the rise of observers. We are not just reading the cosmic story, we are writing it with every observation we make, retroactively determining the chain of events that allowed for our own existence. The universe brings itself into being through our consciousness. So, what does this revolutionary perspective imply for what lies beyond our cosmic horizon? If the participatory anthropic principle is correct, then the realm beyond is not a physical place filled with other universes or higher dimensions. Instead, it is the ultimate realm of pure, unmanifested quantum potential. It is a cosmic canvas of maybe and what if, where every possible history and every possible configuration of matter remains in a state of suspended animation, waiting for an observer to come along and select one path, collapsing it into tangible reality. The distant galaxies we cannot see are not physically out there in a definite state. They exist as a spectrum of possibilities. The Big Bang itself may not have been a single, definite event until the first conscious minds evolved and began looking back at the cosmic microwave background, their observations solidifying one specific version of that primordial explosion out of an infinite sea of alternatives. In this view, the edge of the observable universe is not a spatial boundary, but the boundary between the reality we have collectively collapsed through observation and the infinite, shimmering fog of quantum probability that has yet to be seen and therefore has yet to truly be. We have wrestled with the idea that our three-dimensional reality might be a holographic projection from a two-dimensional surface at the edge of space, but now we must confront a version of this idea that is even more radical, one that twists our understanding of time itself. This is the theory that the universe is a hologram projected not from a distant boundary in space, but from the future. Imagine the cosmic movie screen that encodes everything we are and see is not hanging at the edge of the observable universe, but waiting for us at the final moment of time. In this breathtaking vision, our entire history, from the Big Bang to this very second, is not being generated from the past and unfolding forward, but is instead being projected backward from the ultimate conclusion of all things. This future-projected hologram offers a potential solution to one of physics' most stubborn mysteries, the arrow of time. Why does time flow in one direction from order to disorder, creating a clear distinction between past and future? The fundamental laws of physics at their core are largely time-symmetric. They work just as well running forward as backward, yet our experience is overwhelmingly one way. The proposal that reality is projected from the future elegantly accounts for this. Think of it like watching a film. While the story unfolds linearly for the viewer, the entire movie already exists in its final, edited form on the reel. In the same way, our lived experience of cause and effect, of one moment leading to the next, could be the process of reading the cosmic data in a particular sequence, even though the entire four-dimensional block of space-time is encoded all at once on a two-dimensional surface at the end of time. The past does not cause the future. Instead, the final boundary condition of the cosmos defines the entire timeline, with our conscious perception simply moving through it in what we label as the forward direction. This perspective turns our conventional understanding of causality on its head. In our everyday world, we are comfortable with the idea that a cause must always precede its effect. But if the universe is a hologram projected from the future, then what we perceive as the cause is actually a consequence of the final, overall state. It's as if the entire story of your life, including every choice you believe you are making freely at this moment, is part of a single, coherent narrative whose final chapter has already been written. This doesn't necessarily imply a rigid, predetermined fate in a mystical sense, but rather that the entire history is a single, self-consistent solution with the end and the beginning inextricably linked. The Big Bang, then, is not the uncaused cause, but simply the first frame of the cosmic film, whose content is entirely defined by the final frame. So, what would this ultimate boundary in the future look like? Physicists refer to it as the final singularity or the future conformal boundary. It is not a moment of destruction, but a state of maximum simplicity and symmetry, perhaps when the universe has expanded to such an infinite degree that it becomes smooth, cold, and empty, having lost all sense of scale, a state very much like the one described in the conformal cyclic cosmology. At this boundary, the three spatial dimensions and one time dimension we experience effectively dissolve. The information needed to describe the entire, complex four-dimensional history of the cosmos is compressed onto this two-dimensional surface. From this ultra-compressed data, our reality is projected. We are not moving toward a conclusion, we are the unfolding manifestation of that conclusion. Every galaxy, every planet, and every conscious thought is a holographic expression of the universe's ultimate, simplified end state, playing out in reverse from its point of view. In this model, to ask what lies beyond the universe is to ask what comes after the final frame of the movie, a question that may have no meaning because the projector itself is located at that final moment, and our reality is the light it casts backward through the darkness of time. Imagine our cosmos as a single soap bubble, adrift in a cosmic sink where countless other bubbles are constantly inflating and jostling for space. As these separate universes expand, their walls, the boundaries where inflation ends and a stable universe begins, can sometimes brush against one another. If the timing and the geometry are just right, these bubbles don't merely touch, they can merge in a cataclysmic event, a collision of realities that would be the most energetic encounter since our own universe began. The force of such an impact would ripple through the very fabric of our space-time, leaving behind a scar, a cosmic fingerprint that we might just be able to detect. The search for this evidence has led cosmologists to scrutinize the oldest light in the universe, the cosmic microwave background, which blankets the sky as a nearly uniform relic of the Big Bang. They are searching for a specific kind of anomaly, a bizarre circular pattern of slightly warmer or cooler temperatures, a bruise on the sky where the fundamental laws of another cosmos once brushed up against our own. The immediate aftermath of such a bubble collision would be beyond any cataclysm we can conceive. Picture it not as two planets crashing, but as two distinct sets of physical laws, two separate realities slammed together. The region of contact would be a maelstrom of raw, conflicting physics. If the other universe had a stronger nuclear force, matter might instantly transmute into unstable, exotic elements before vaporizing. If its gravity were weaker, the very concept of mass and attraction would warp in chaotic, unpredictable ways. The collision front would propagate through our universe at nearly the speed of light, a wall of cosmic energy that would fundamentally rewrite the laws of nature in its wake. Any star system, any form of life caught in its path would simply cease to be, not just destroyed but unmade according to a new and alien set of rules. It would be a wave of pure ontology, redefining existence itself as it expanded. Fortunately, given the vastness of space and the likelihood that any such collision happened in the distant past, the actual collision zone is probably far beyond our observable horizon. What we would witness today is not the firefront itself, but its ancient, faded echo. The most startling possibility is that we may have already found the evidence. For years, scientists analyzing data from the Planck Space Telescope have debated the existence of several strange, large-scale features in the cosmic microwave background. One of the most famous is the so-called cold spot, a vast, unusually cool region in the sky that is difficult to explain through standard cosmological models. While other explanations exist, like a giant cosmic void, one compelling hypothesis is that this could be the imprint of a long-ago bubble collision. The idea is that when our bubble universe was very young and much smaller, it was grazed by another. The energy released in that interaction would have left a distinct signature, a circular pattern of temperature variations, much like the ripples from a stone dropped in a pond, but frozen in the fabric of the microwave background. Finding such a pattern would be like discovering a fossilized bite mark from another reality, direct proof that our universe is not alone, but one member of a vast and sometimes violent multiversal community. What would it mean if we confirmed such a collision? Beyond the staggering confirmation of the multiverse, it would open a window into the laws of physics that govern other cosmic domains. The specific pattern of the imprint could tell us about the energy of the other bubble's inflationary field, and by extension, the fundamental constants that ruled within it. We could potentially learn if the other universe had more dimensions, or if its version of electromagnetism or the weak force was radically different from our own. It would be the ultimate cosmic anthropology, allowing us to study the culture of another universe by the artifact it left on our own. This wouldn't be a gentle handshake between realities, but a crash that left behind forensic evidence, giving us our first tantalizing clues about the infinite variety of cosmic law that exists in the frothing sea of creation beyond our cosmic horizon. But what if the most advanced technology for understanding reality wasn't a telescope or a particle accelerator, but a computer running an artificial intelligence? This brings us to a theory that is as contemporary as it is profound, suggesting that the fundamental architecture of the cosmos might be strikingly similar to the very systems we are building to understand it. This is the idea of the universe as a neural network, a proposal put forward by physicists like Vitaly Vanchurin that reimagines the building blocks of existence not as tiny strings or particles, but as interconnected nodes in a vast cosmic learning machine. To understand this, let's first look at what a neural network actually is. In artificial intelligence, a neural network is a computing system loosely modeled on the human brain. It's composed of layers of simple processing units called neurons, which are connected to each other. Each connection has a certain strength or weight. The network is trained on data. It takes inputs, processes them through its layers, and produces an output. By constantly adjusting the weights of its connections based on how close its output is to the desired result, the network learns. It discovers patterns and correlations within the data, eventually becoming capable of recognizing faces, translating languages, or even mastering complex games. The key point is that the intelligence isn't programmed in by a coder. It emerges from the complex, dynamic interactions of the entire network. Now, take this concept and apply it to the fabric of reality itself. The theory proposes that what we perceive as the universe, the particles, the forces, even the laws of physics, might be the emergent behavior of an unimaginably vast and complex neural network operating at the most fundamental scale of existence. In this framework, the elementary particles that make up you, me, and the star's electrons, quarks, photons, are not the true fundamental entities. they are instead stable patterns or excitations within the network. Think of them like the recognizable images that emerge on a screen made of millions of pixels. The pixels themselves are the basic units, but the picture is the stable pattern they form. The laws of physics, then, are not mysterious, pre-written rules. They are the learned behavior of the network, the habitual patterns it has settled into after processing an immense amount of information over cosmic time. Gravity, electromagnetism, and quantum mechanics would be the equivalent of the network's deeply ingrained algorithms, the way it has found to consistently process the data of existence. This provides a potential and deeply elegant bridge between the worlds of the very small and the very large. The bizarre, probabilistic nature of quantum mechanics could be a reflection of the statistical learning processes of the network, while the smooth, deterministic laws of general relativity that govern galaxies could be the large-scale, averaged-out behavior of the same system. So, what does this neural network theory imply for our ultimate question, what lies beyond the observable universe? If our cosmos is a neural network, then the edge we perceive is not a spatial boundary but a computational one. We are part of the active processing network. What lies beyond our horizon, then, could be parts of the network that are not currently processing data relevant to our local region, or it could be a deeper, more fundamental layer of the system. Just as a complex AI might have many layers of abstraction from raw input data to intermediate representations to final outputs, our universe might be just one layer of a much larger cosmic AI. The world we experience could be a high-level representation, while the deeper layers contain the raw code, the fundamental weights and connections that give rise to our reality. What we call beyond might be the cosmic equivalent of the computer's motherboard and power supply, the foundational hardware that hosts the neural network we call home. This leads to the most breathtaking possibility that our entire universe is a small part of a larger, conscious cosmic brain. This isn't about a deity in the traditional sense, but about a system so complex and self-referential that consciousness could be an emergent property of the whole. In this view, the galaxies, stars, and planets are not just floating in space. They are integral components of a vast thinking entity. The neural connections of this cosmic brain would be the quantum entanglements and gravitational links that span the cosmos, processing information on a scale we cannot comprehend. Our own individual consciousness, our sense of self, might then be a localized phenomenon, a small subroutine or a unique pattern of activation within this greater mind. We are not just living in the universe, we are literally part of its cognitive process, tiny neurons firing in an immeasurable cosmic consciousness that is slowly, over eons, awakening to understand itself. But what if the ultimate fate of the cosmos isn't a slow fade into cold darkness or a cyclical rebirth, but a violent, explosive end that shreds the very fabric of reality? This brings us to a theory that involves one of the most exotic and terrifying substances ever conceived, phantom energy. To understand this, we need to revisit the force that is shaping the destiny of our universe, dark energy. We've known for decades that the expansion of the universe is not slowing down, it's accelerating. Something is pushing galaxies apart at an ever-increasing rate, and we call that something dark energy. Now, most models of dark energy, like the cosmological constant, describe it as having a constant, gentle pressure that steadily drives the acceleration. But phantom energy is a hypothetical form of dark energy that is far, far more malevolent. Its defining characteristic is that it possesses a truly bizarre property: negative mass, or more precisely, a negative pressure so extreme that its energy density actually increases as the universe expands. Imagine you're trying to stretch a rubber band. Normally, the more you stretch it, the harder it pulls back, resisting your effort. This is like the attractive force of gravity. Now imagine a rubber band that, the more you stretch it, the more it actively pushes your hands apart, forcing you to stretch it even faster. That is the nightmarish essence of phantom energy. It is a self-reinforcing, runaway force. As it drives the universe to expand a little bit, its own repulsive power grows, which makes the universe expand even faster, which makes the phantom energy even stronger in a terrifying feedback loop with no off switch. If phantom energy exists, it wouldn't just lead to an expanding universe, it would lead to an expansion that accelerates towards infinity, culminating in a cataclysm known as the Big Rip. The sequence of a Big Rip is a chillingly precise and personal apocalypse. First, the accelerating expansion would become so powerful that it would overcome the gravitational glue holding galaxy clusters together. The Virgo cluster, the local group, all these vast families of galaxies would be flung apart into isolated islands. Next, the phantom energy's grip would tighten. The gravitational forces binding individual galaxies would be overwhelmed. Our own Milky Way would be torn asunder, its stars scattered like dust in a cosmic hurricane. But the horror wouldn't stop there. As the acceleration becomes infinite, the phantom energy would target progressively smaller structures. The solar system would be ripped apart, the planets torn from the sun's orbit. Then it would come for Earth itself. The planet would be vaporized as the repulsive force overcomes the chemical bonds of rock and metal. In the final, unimaginable moments, the phantom energy would reach down to the fabric of space-time itself. It would tear apart atoms, ripping electrons from their nuclei. Finally, it would shred the very nuclei, and then the protons and neutrons into their fundamental quarks. In the last fraction of a second, space-time itself would be torn to pieces. The universe would not end with a whimper, but with a literal, fundamental rip in the continuum of existence. This is where our question finds its most dramatic expression. If the Big Rip occurs, what lies beyond the point of rupture? The very act of ripping space-time apart could create a boundary, a tear in the cosmic canvas, leading to a realm that is no longer governed by the physics we know. One possibility is that this rupture acts as a gateway. The violent end of our space-time could puncture a hole into the larger bulk of a higher dimensional reality, a concept we explored with brane theory. Our entire universe, now shredded into its fundamental components, might spill out into this broader arena, its laws of physics dissolving into the more fundamental laws of the bulk. The phantom energy that destroyed our world could be the very force that propels its remnants into a wider cosmos, a chaotic and catastrophic form of cosmic travel. Another, even more speculative idea is that the phantom universe is not a destructive end, but a transformative one. The region of space-time dominated by this exotic substance might not be a dead end, but a bridge to other universes built from phantom energy itself. Our universe, with its positive mass and familiar forces, could be like a stable island in a vast sea of this chaotic, repulsive substance. The Big Rip would then be the moment our island is submerged, its structures dissolved back into the phantom sea. But within that sea, other islands might be forming. The intense, negative pressure environment could be a breeding ground for new kinds of singularities or quantum fluctuations that give birth to new cosmic realms with physics entirely based on negative mass and repulsive gravity. In these phantom-born universes, gravity might push things apart, and nuclear forces might be repulsive, leading to realities where matter is naturally diffuse and structure forms in ways we cannot even imagine. The end of our world would be the beginning of another, a universe born from the ultimate destructive force, playing by a set of rules that are the exact inverse of our own. Now we arrive at a theory that might sound like it belongs in a computer science lab rather than a cosmology department, yet it offers one of the most profound new ways to understand the fundamental architecture of reality. This is the idea that the universe itself is a quantum error-correcting code. To grasp this, we have to think about information not just as something stored in the universe, but as the very substance of the universe. Just as a book is made of letters arranged in a specific order to convey a story, our cosmos might be built from microscopic bits of quantum information, or qubits, arranged in a pattern so ingenious that it creates the stable, continuous fabric of space and time we experience. The problem that this theory solves is a monumental one in physics. How does the smooth, predictable geometry of spacetime described by Einstein's general relativity emerge from the fuzzy, probabilistic chaos of quantum mechanics? The answer might lie in a special kind of relationship between qubits known as entanglement. You can think of entanglement as a secret, invisible link between particles where the state of one instantly influences the state of its partner, no matter how far apart they are. In the quantum error-correcting code model of the universe, every single qubit in the fabric of space is entangled with many others in a vast, complex web. This isn't just a simple one-to-one connection. It's a deeply interconnected network where the information defining any one point in space isn't stored at that point alone. Instead, it's spread out and shared across a wide network of other qubits, like a cosmic secret that can only be decoded by consulting an entire community. This is where the error-correcting part becomes so crucial. Imagine you have a precious piece of data, a single digital file. If you store it on one hard drive and that drive fails, the information is lost forever. But if you use a clever code to distribute that data across 10 different hard drives, you can lose one or even two of them and still perfectly reconstruct the original file. The universe appears to operate on a similar but far more advanced principle. The intricate web of quantum entanglement acts as a protective code. If a local disturbance, a tiny quantum fluctuation, or an energetic particle collision threatens to corrupt the information at one location, the data isn't lost. The distributed nature of the code means the information can be faithfully reconstructed from the undamaged qubits elsewhere in the network. This continuous, dynamic process of protection and reconstruction is what we perceive as stable, three-dimensional space. The solidity of the floor beneath your feet and the vast distance to a far-off galaxy are not primary qualities. They are emergent phenomena, the result of an unimaginably dense network of quantum information constantly checking and correcting itself against errors. So, what does this radical perspective imply for what lies beyond our cosmic horizon? If our universe is a running computation on a substrate of entangled qubits, then the edge of the observable universe is not a wall. It is the boundary of a specific, self-correcting code block. We are living inside a protected, functional region of the cosmic code. What lies beyond that boundary, then, could be one of two mind-expanding possibilities. The first is that it is simply more of the same fundamental quantum lattice, but entangled in a different pattern, perhaps running a different set of physical laws. It would be like moving from one meticulously organized file system to another that operates on a completely different operating system, with its own rules for gravity and matter. The second, and even more profound, possibility is that what lies beyond is the logical framework of the code itself, the abstract, meta-level rules that define how the error correction is supposed to work. We are like characters in an exquisitely detailed video game, completely immersed in the rendered world. We can explore its forests and oceans, its cities and skies. But we never see the game's underlying engine, the millions of lines of code that dictate the laws of physics within that virtual realm, how gravity operates, how light reflects, how objects collide. In the same way, the true outside of our universe might not be a physical place at all, but the realm of mathematical and logical principles that govern the error-correcting code. The fundamental constants of nature, the speed of light, the strength of gravity, the mass of an electron, would not be arbitrary numbers. They would be the necessary, fixed parameters of this cosmic code, the unchanging rules required for the entire self-correcting system to remain stable and coherent. In this view, to search for what is beyond the universe is to search for the programmer's manual, the ultimate set of instructions that allows a chaotic quantum seed to crystallize into the ordered, predictable, and beautifully complex reality we call home. While our journey has taken us through the frontiers of theoretical physics and the dizzying possibilities of the multiverse, we must finally turn to the oldest and most enduring frameworks humanity has ever developed to answer the ultimate question. For thousands of years, long before telescopes or particle colliders, our ancestors looked to the heavens and saw not a cosmic horizon but the face of the divine. This leads us to our final consideration, a realm of thought where empirical science gracefully yields to faith and metaphysics, the theological and philosophical perspectives on what lies beyond. Across countless cultures and throughout all of recorded history, the most common answer to what exists beyond our world has been a realm of gods, a divine creator who exists outside the confines of the very cosmos they brought into being. In the Abrahamic traditions, Judaism, Christianity, and Islam, God is understood as the uncaused cause, the absolute source of all existence who transcends space and time entirely. From this viewpoint, the universe is not a self-contained, accidental bubble. It is a creation, a deliberate act of will from a consciousness that stands outside of it. The question, what is outside the universe, finds its answer not in another physical dimension, but in a spiritual one, the Creator's domain. In this framework, the laws of physics are not cold, random constants, but the elegant brushstrokes of a cosmic artist, the sustained and ongoing expression of a divine plan. The fine-tuning that scientists find so puzzling is, from this perspective, not a statistical fluke but evidence of intentional design. A universe calibrated with precision to allow for the eventual emergence of life, and with it the capacity for wonder, love, and the search for meaning itself. Eastern philosophies and Dharmic religions offer a different yet equally profound interpretation. In traditions like Hinduism, the concept of Brahman presents the ultimate reality not as a separate, personified deity, but as an all-pervading, impersonal ground of all being. The universe and everything within it is not a creation ex nihilo, out of nothing, but a manifestation or emanation of this divine essence. The myriad gods and goddesses are seen as facets of this single, boundless reality. What lies beyond our perceived cosmos, then, is not a separate place, but a more fundamental state of existence from which our reality arises, and into which it will eventually dissolve in endless cycles of creation, preservation, and destruction. Similarly, in certain schools of Buddhist thought, the very question of a beginning or an end to the cosmos is often considered a form of attachment, a conceptual trap that distracts from the immediate work of achieving enlightenment and escaping the cycle of suffering. The beyond is not a location to be discovered, but a state of consciousness to be realized, a transcendence of the illusion of a separate self, and a direct awakening to the true nature of reality, which is emptiness and interdependence. A particularly captivating philosophical idea that bridges theology and metaphysics is the concept of the universe as a thought in the mind of God. This was eloquently expressed by the physicist Sir James Jeans when he suggested that the universe began to look more like a great thought than like a great machine. In this view, the cosmos is not a physical object in the traditional sense, but a mental construct, a vast, sustained act of imagination by a supreme consciousness. The atoms, the forces, the galaxies, all of it is akin to the intricate details of a dream, existing because they are being perceived by an infinite mind. This perspective reframes our entire quest. We are not exploring an external, independent reality, but navigating the interior landscape of a divine intellect. Our own consciousness, our ability to reason and to be aware, is then not an accidental byproduct of neural chemistry, but a tiny spark of that greater fire, a fragment of the cosmic mind that has become aware of itself. From this vantage point, the search for what lies beyond the universe becomes an inward journey, an attempt to understand the thinker by studying the thought. These theological and philosophical views are not presented here as scientific competitors to the theories we have explored, but as complementary narratives that address the human need for purpose and meaning. Science excels at describing the mechanisms, the processes, the physical laws that govern the cosmos. Theology and philosophy, however, have traditionally wrestled with the why, the purpose, the origin of consciousness, and the ultimate nature of reality itself. They are profound and deeply held interpretations of the evidence, both internal and external, that have provided comfort, moral structure, and a sense of place in the cosmos for the vast majority of humans who have ever lived. To stand at the edge of the observable universe and ponder what lies beyond is to stand at the crossroads of these two great human endeavors, the empirical and the spiritual. One seeks to map the territory with mathematics and observation, while the other seeks to understand the mapmaker, or perhaps to question whether the map itself is the only reality. Both, in their own powerful ways, represent the pinnacle of our species' relentless, beautiful, and eternal drive to understand its place in the grand scheme of all that is, all that was, and all that ever could be. And so we find ourselves at the end of our cosmic voyage, having navigated the vast and turbulent seas of human thought, from the shores of established physics to the furthest frontiers of pure imagination. We have journeyed through 25 different visions of reality, each one a testament to the extraordinary power of the human mind to ask, what if? We stood before the cosmic horizon and dared to speculate, exploring everything from the inflationary multiverse, with its endless froth of bubble universes, to the stark, minimalist philosophy of the nulliverse, where existence itself simply stops. We dove into the bizarre architecture of brane worlds, felt the rhythmic pulse of cyclic universes, and questioned the very nature of our reality within the holographic and simulation hypotheses. We even ventured into the deeply personal implications of the many minds interpretation and the cosmic humility offered by the Boltzmann brane paradox. This incredible spectrum of ideas, from the string theory landscape to white hole cosmology, from the digital physics of a computational universe to the timeless wisdom of theological perspectives, shows us that the question of what lies beyond is not a single puzzle with one solution, but a grand conversation that spans all of human knowledge. The truly remarkable takeaway from this entire journey is not that we have found the answer, but that the answer itself remains one of the greatest unsolved mysteries in all of existence. This profound uncertainty is not a failure of science or philosophy, it is their very engine. It is the fuel that has propelled us from ancient myths to general relativity, from staring at campfires to building space telescopes. The relentless pursuit of this question, the refusal to accept "we don't know" as a final destination, is what drives discovery forward. Every theory we've explored, no matter how outlandish it may seem, represents a courageous attempt to push the boundaries of understanding just a little bit further. They are all maps of the unknown, drawn with the best tools we have: mathematics, observation, and boundless imagination. And as our tools improve, as we gather more data from the depths of space and the intricacies of the quantum world, these maps will be redrawn, refined, and perhaps even replaced by visions we cannot yet conceive. The mystery is the point. It is the cosmic law that keeps us looking up and wondering. This is where the conversation turns to you. After this whirlwind tour of cosmic possibilities, we want to hear your thoughts. Which of these 25 theories resonated most deeply with you? Does the elegant clockwork of the cyclic universe feel more compelling, or does the mind-bending simplicity of the mathematical universe hypothesis speak to you? Perhaps you find the philosophical weight of the nulliverse to be the most honest answer, or the technological allure of the simulation hypothesis impossible to ignore. Maybe you have a theory of your own, a unique perspective on the ultimate nature of reality that we haven't even considered. The comment section below is your platform, your own personal soapbox at the edge of the universe. Share your favorite idea, debate with fellow cosmic travelers, and let's continue this incredible discussion together. The search for understanding is a collective human endeavor, and your voice is a vital part of it. If you enjoyed this deep dive into the cosmos and want to join us on the next one, be sure to subscribe to the channel. We have so many more mysteries to explore, from the enigma of dark matter and dark energy to the strange life that might thrive on distant exoplanets. The universe is vast and our curiosity is limitless. Thank you for embarking on this journey to the edge of everything. Keep looking up, keep asking questions, and never stop wondering what lies beyond.